What's up, everyone? Welcome to the new mini series where I'm going to teach you how to write a bootloader from scratch. In this video, you will learn about how boot sequence looks like and what a real mode is, and you will write your first bootable code. This series will consist of 3 videos, and by the end of it, you will have a fully working bootloader that will load a 32-bit kernel capable of displaying messages on your screen. And you don't want to miss it, so make sure that you hit that subscribe button, and let's get started. Let's start by answering a simple question: what happens when you power on your PC? All starts with a post or power on self-test. Power supply sends power to all the components. Then BIOS firmware takes control and it initializes CPU memory and hardware components to post checks for hardware errors such as checking memory and ensuring all the essential devices are operationals. Then BIOS where code is copied from ROM to random access memory, or you can say it as RAM also, for faster execution. Once all that is done, a search for bootloader begins, where BIOS checks the boot order setting to find the boot device. The firmware looks for the master boot record, which is first 512 bytes of boot device, also called the boot sector. It identifies it by looking at the last 2 bytes, which are 55 and AA, respectively. Once the bootloader is located, BIOS loads it to the memory and execute the code. Now that you know the basics of BIOS boot sequence, let's talk about a real mode, which is 16-bit mode, in which all x86 CPUs start their execution. Later on, they switch to protected mode. But we are going to talk about protected mode in next video. So right now we are talking about real mode. So real mode is something which where memory access is handled using segmentation. We have little over 1 megabyte of addressable memory in format of segment offset, and a 16-bit segment address is stored in one of the segment registers. This is basically a starting point of a segment, and 4-bit offset value which is stored in one of the general purpose registers. So in the total we have 20 bits, 2 to the power of 20. So roughly it should be 1 megabyte. Now for calculating the physical address, you can use this equation. We are taking the base address of a segment, multiplying it by 16, which is equivalent to shift left by 4 operation. So we are sort of making space for the offset. This is like an explanation for those who don't really get the hex map thing, but it's okay, you don't need to know it perfectly. But anyways, to this you can you add an offset, and you have the physical address of the exact location memory that you want to access. You also have to know the real mode is secure, is not secure, and at all. And when CPU runs on it, a user program can impact kernel in such way that it can completely destroy it. All right, so enough theory for now, and let me show you some tools that you need to install before performing this action or making a bootloader from scratch. Okay, so let's get started with the code part. So firstly you should open your terminal, and after opening your terminal you just need to install assembler first. So the command for that is sudo apt install nasm. I already installed that, so it will just show me like my newer version or something else. And after that you need to install one more thing, that's a qemu system x84 thing. So this is already installed in my system, so you just need to copy these commands and paste in the system. And after that we should make a folder structure. So for folder structure, I already made a folder inside my document files. I just open that. Okay, so now we are inside a folder, and we can see that there is nothing as here. So let me maximize it. Okay, so now we have to create two folders, like one is for binary and one is for source file. So let's create that folder. So for making these folders, you just use one command, make directory bin and source. And we also need one file also that's name as make file. So for a make file we can just use touch. Okay, so our folder structure is kind of ready right now. Sorry. One more thing we have to do, we have to make a boot.asm file inside the source file. So let get inside the source and git touch boot.asm. Now our folder structure is totally ready. So you can open any of your favorite id right now. So I will open my favorite id, that's zid. So just now we will start with the project from there. So actually why we had done this, so let me go like we have made a folder as bin to store binaries and the folder called source to store source files. This is a like sort of elegant way to handling our project in a very necessary like it's a very necessary also, because this is going to be a very small project, right? But it is just good to have this habit of sorting files. Let me make. No, we don't need to make anything. Okay, so we have all the files right now. So that boot.asm file is already are inside the source directory. Actually, why we did this? We actually did this because it will allow us to compile and clean project much quicker, and this it is going to be a lot more elegant sort of way if you need to compile a lot of files at the same time. It's easier to just type make all instead of compiling each file like you will do na each file like again and again. Instead of that, you can just write a simple function in the make file. All things will compile on the basis of that easily. And one more thing, there are a lot of files at the same times. That's the thing. Like it will make it easier. So separately, so this basically allow us a little gives and little automation. But don't worry if you never used it. I'm going to show you like line by line how to do it. Okay, so let's start writing the code. We want to start specifying that we are in 16 bits. 16 bits. Like this is the origin of the code. Like how we written the origin of the code. Like I will show you. So first of all, you had to write bit 16. Wait, inside the square brackets. Okay, one more thing, like how we can give the commas, like not commas, comments to the assembly language. So you just use this semicolons to give comments. So I will write the comment. It will actually set the code to 16-bit. And after that, like we will start with our origin. Sorry. Okay, so what is this? Like this is an origin. Like we are setting the origin, like it's the starting address, which is starting from 0x7c00. Actually I have written this wrong. It's a hexadecimal thing, so you need to take care of that. It's a case sensitive. The language is not case sensitive, but you need to write the hexadecimal values in the exit format, like what is written there. So basically what it does, it's just set the origin, or like typical for boot loaders. So now we will start with our CLI. Actually what it does, it clear the interrupts. Now we will assign our registers. Like one thing about the Z Studio, like ZID, you don't see any prettifier thing. Like in VS Code, we have something called prettier, which make our like I have given this, so it should make a indentation and move it to this side, but it doesn't. But that's because of that. Like it is because maybe this is a new ID and there is no functionality like this. Okay, so if you are like like you have you are like friendly with assembly a little bit. So what we are doing here, we are just shifting this address inside the AX, and from there we are shifting AX to DS. Like if you just compile with these two, both values of these two are like will be same, because we have given this to this. So right now AX is equals to this one. So if you do a manual calculating, this is a 0x00 and you are giving it to this. So what is happening here, this value is shifting to these registers for the allocation of this. After that we had took we should take another register ES. Like I have explained these things in my video also, like what are this, like DS, ES, and basically these are the segments we are taking. Data segment, I forgot the name of this one, but it's something. Hmm. We will check it out later. Oh, sorry, yeah, it's the extra segment, and this is data segment. And like what we are doing, we are setting data segment to this one. Okay, so after that what we had to do, we just write AX again and move SS. What is SS? SS is something which called as a stack segment, and SP is a stack pointer. You will learn it later in your classes also. Like we have subjects called microprocessor and controller. You will learn about stack pointer there also. But what's happening here? Actually, what you are doing? We are setting the stack pointer like SP to this value. So at the top of the bootloader segment, like we have to, like we are setting this as the top of the bootloader segment. Like if you have like a knowledge of knowledge of some hexadecimal, you will get to know like what I have written here. Like it's something related to your bias, and you will learn it later. Okay, so this MSG refers to the message. So basically, what it does, it load the address of the th move the mood sorry load the address of that message into the source index. Like basically SI refers to source index. And now we will write STI. What it does actually, it enables interrupts and all owing them to occur them again. Now we should print that we will use a load sp. Basically load sp refers to the load byte, as we are using data segment and segment sorry data segment and source index integer to al register and increment it to another thing. Okay, so right now, if you are like showing like what's the meaning of this, so basically CMPAL tends to zero. It refers to, like we are comparing. Like CMP refers to comparing the value of value in A with L. This like value of this one to this with a null terminator. What is null terminator? We can call 0 as the null terminator. And right now in the 18th line we have JE command. Basically what does it mean? So JE command is just a simple thing. You are jumping to the done, that's a JE. But if you like use ARM 86 assembly programming, there is one more command for jumping, that's JMP. So we will discuss this later, but right now we will do this also. Now we will move our age register to 0x 0e. Basically, what happens here, it will set age register to 0x 0e. Actually, this is the bias teletype output function. You will get to know in this documentation. Wait, I will show you. Like what we are using 0x10, right? So we have many functions here, so you can check it out. Like we are using the e1, so it actually used for displaying the char, so we are actually printing the hello world there. So that's why I'm using the int 0x10 as the bias output teletype function. As I explained, like why we are using this. So basically what it does, like, let me write the command for that. Okay, so like after that, we will now jump, like we will actually use our jump command. So right now what this jump do, actually it will jump back to the print and label the process to the next character. It will just jump back to the print and label the character like we are using to print here. Like we will sort of using a message command to message our next thing which we give to this MB, like a DB thing. Like I will explain what is DB. DB is something like define character, but it's like DB, but mm, I will explain it later. We will done about this and CLI. Actually, it's like what does it CLI mean? CLI is like clear interrupts. You can understand from CL. CL is for clear and I for interrupts. It's not the CLI we are using for the terminals. It's little bit different from them. It's like disabling all markable interrupts or anything. And we have one more thing, halt. Like we will stop there. Like we will halt the CPU after this command. So right now we have to type a message command which will display hello world. Actually, it defines the message hello world followed by the null terminator. I already explained you previously what is zero. Zero is nothing but the null terminator. Now we will just do one more thing times 5 or 10. Like I will explain like what is this. Actually, times 510, it actually fills the spaces like we are lefting out. For example, if you are like getting something and you are sort of like cutting them, but there are some spaces left out, so you just have to fill them spaces. So we just for filling this that spaces we uses these things. And like if you basically the syntaxes of assembly are too different. For new line you have to use an hashtag 10 thing, so you can get a better understanding like we are not using characters here, we are just using numbers like which are actually going to do this task for us. Again, so basically what it does, like let me explain again. It will fill the rest of the boot sector. I have already explained what is boot sector. Like boot sector is something which contain 512, like first 512 bytes of the 55 and a thing. So like it's kind of database where the first two like sectors are filled with 555 and a hexadecimal values. And there's a sorry. And one more thing, that boot sector it's filled with the zeros up to 510 bytes. Like we are giving this, so actually the null terminator is acquired to give it 510 bytes, so it can fill all the spaces which comes under 510 and 512. Now we will end it with dw. 0 x AA 55, as we discussed in our sector boot sector. So actually what this is, it's a boot sector signature required to make the disk bootable. So right now we have completed the code for bootloader only for the is boot file. Okay, so now we will write a command for a make file to execute it inside a thing. Okay, so for executing it, you just need to write a make file thing. It's simple basically. All you have to do is just write a all command, and okay, so that's our executing thing. Like I will go through that. Like I will let you go through that. Okay, so the thing is like how you run this command right now, right? So let us check like how we should run this. So before that, I just need to tell you the one thing. Like we have the bin folder. Actually, we are setting here the path. Like NSM is assembly compiler or like assembler. What it does, it actually removes like force removes the thing and added the inside the bin folder. Inside the bin folder, it actually take data from the this thing like from source boot.asm and make a boot.bin file inside that, which you can see using one thing like let me show you something called as like I have the application for that. The application is known as blast. Yeah, blast. For that you just need to do one thing. You have to like write a sudo apt install blast, and you will like get like you will just download this command from there. And for running this, mm, let me like think about like how we run this thing. Like we do something like with ls, we have make file inside that. So for running that make file, okay, so that's the code right now. If you wanted to print that, so we will write QUME system x86 underscore 64. Then we will write maybe hta slash boot dot bin. What it says, no such file or directory we have here. So just wait for that. Like maybe I'm forgetting something. Okay, let's open this thing in VS Code. Okay, so let's begin with this. Hmm. So now what we have to do, we have to use makecli. So what it shows, makecli, make file missing separator. I got to know like the indentation is wrong something. So let me like just take it through my previous code. Oh no, no, we just do something else, right? Instead of this, we can just. Okay, so now for compiling this code, we have written here. So first of all, just we need to do just one thing: opening our terminal. From there, like we have opened our terminal, and just you can see that we don't have any file inside this bin. So what we need to do is like we have to make that. Okay, so we have like we get a file inside that. We can can't open that because this is in the UTF-8 format, and this is sorry, this does not contain any UTF-8 format. So if it is in UTF-8 format, we can easily see that in Notepad thing. But for that, for seeing this, we just need to use bless. So let's go through that. Inside this, what you need to do is cd bin. You have to go inside the bin folder from there, like cd bin. And when you get inside this, you can click ls to take whatever file inside that. And if you want to check like what does this binary code say, so you just need to use blast boot.bin. And this thing is known as blast, and what it does, you can see your 55 and 80 thing, like what is this actually. I already mentioned you that that's the boot sector. That's the first two bytes, like first two byte between the 511 and 512. All this contains or starts from there, like 55 80, and this is called as the boot sector. So we are printing the hello world, and it's like compiling inside the machine and printing like this. So like how we should display it, so let me use, let me show you. Before that, how you can install that. Okay, so you can install blast just typing sudo app install blast, enter password, and you'll get to solve the whole thing in easy way. Now the things comes to like where is our bootloader. Sorry. So let me show like where is our bootloader. So for that, we just need to write a command which is q e a o s system x86 underscore 64. I already told like what is x64. Actually it's the architecture of our PC 64-bit system. After that, you have to write HPA. H refers to something hardware definition language, and we have to write about that boot.bin. Which actually we are here. We are executing our boot.bin. So that is something. Okay, so this is our bootloader actually. It's a basic bootloader. You can see here, like we have the machine thing also. Like our mouse is not working here because we just need to press on Control Alt plus G. If we press on that, our mice will be blinking. Okay, so our mice is working right now. So you can just pause, quit, and power down from that. Like if it is like completely ready, so what you can do that, like you can just start booting from there. So that's all the basics for basics and the something which can call like it's a basic bootloader for our system. So after that, we will proceed with the second part. In second part, like we have like here we have learned about the real mode. Today we have learned about the real mode. It's not that much secure. Like if you just letting your root.bin, it will totally forget your system. But in protected mode, we have some sort of things which can help us to perform more actions and more good thing. Like it's protected mode. Like you maybe have learn things in C++ like about public, protected, and one more thing private. So we have the same things in this. Like in Oops concept, you have learned about that. So in this thing, I am teaching you like how you can make three types of bootloader: public, protected, and private bootloader. In same case, like the private and protected is little same. Nothing just happened there. So that's it for today's video. I hope you guys like it. And if you have any doubt, you can check my repository for the code, and we will sort of like comment like whatever the mistakes you find in this video, and you want more things to change in me. Thanks.